Due to COVID disrupting students' education for the 2022 summer GCSE exams, the exam boards have released an advanced notice article that gives an insight into what will be on the exams this year. I'm sure your teachers have shown you this article already. In this version of the advanced notice article, I'm going to show you anything in green is definitely going to be on the exam. Anything in yellow may be on the exam in a small way, and anything in red will not be on the exam. In this video, I'll go over the green and yellow areas to help you prepare for the Triple Physics Higher Paper 2 exam. So for Paper 2, here's SP8 Energy Forces doing work. You're supposed to be able to describe the changes involved in the way energy is stored when systems change. So what that means, when a system changes, that could be a car braking, which would be kinetic energy stored in the car getting turned into heat energy stored in the brakes. It could be a light bulb, where there'll be electrical energy getting turned into light and heat energy. Draw and interpret diagrams to represent energy transfers. So an energy transfer diagram, for example, for a bulb would be electrical energy going in and it's getting converted into light, useful energy, and heat, which is wasted energy. Explain that where there are energy transfers in a closed system, there is no net change to the total energy in that system. What that basically means is what goes in must come out. So it's the law of conservation of energy. For example, if 200 joules of electrical energy goes in, 200 joules needs to come out. Now, not all of the energy that comes out will be useful. There's only 80 joules here that's actually useful. 120 joules is being wasted. But it's still there. 200 went in and 200 came out. You just can't use this wasted energy for any further useful energy transfers. Identify the different ways that the energy of a system can be changed through work done by forces, which basically means mechanical work. And that's when a force moves an object through a distance. Using this equation, work done equals force times by distance. Electrical equipment. So electrical work, for example, could be charges moving due to a potential difference or voltage. And heating, well, that would be something like heat energy transferring from one place or object to another due to a temperature difference, which can be caused either electrically, but from current, or by chemical reaction, for example, burning a fuel. Describe how to measure the work done by a force and understand that energy transferred in joules is equal to work done. There we go. Energy transferred is equal to work done. Now remember, work done is force times by distance if you're talking about it in a mechanical sense. In other words, when you're moving things. Recall and use the equation work done equals force times by distance. So there it is there, W equals F times by D. But you could also say it as E equals F times by D, because remember, work done equals energy transferred. So it's just a case of you putting the numbers in. Describe and calculate the changes in energy involved when a system is changed by work done by forces. So in other words, it's just energy transferred equals force times by distance. So they'll just give you the numbers, you've just got to pop them into your calculator. Recall and use the equation to calculate the change in gravitational potential energy. So again, it's just this equation, and you've just got to pop the numbers in. So the change in gravitational potential energy equals mass times by gravity times by change in height. Recall and use the equation to calculate the amount of energy associated with a moving object. In other words, you've got to be able to calculate kinetic energy using this equation. Kinetic energy equals a half times by the mass times by the velocity squared. Make sure you square the velocity first before you do anything else. Explain using examples how in all system changes energy is dissipated so that it is stored in less useful ways. In other words, you always lose energy as heat and sound, and it goes to the surroundings. And that's usually because of friction. Explain that mechanical processes become wasteful when they cause a rise in temperature, so dissipating energy in heating the surroundings. Well, that's what I've just said there. Mechanical processes, in other words, it's friction. When objects move and rub, it causes heat and sound, which dissipates to the surroundings. Try to memorise that statement there. It could be worth up to 3 marks. Define power as the rate at which energy is transferred and use examples to explain this definition. For example, that ties straight in with this equation. The power equals energy transferred over time. Power is measured in watts and energy is measured in joules and time is measured in seconds. So 1 watt is equal to 1 joule per second. And there we go there. Recall that 1 watt is equal to 1 joule per second. And recall and use the equation for efficiency. So efficiency equals useful energy transferred by the device divided by the total energy supplied to the device. For example, a bulb. If we put 200 joules of electrical energy in and 80 joules gets turned into useful light and we've wasted 120 joules, to get the efficiency you do the useful energy that came out divided by the total energy that you had to put in. So in other words, 80 joules of light energy came out, we had to put 200 joules in, 80 over 200 comes out as 0.4. Now if the examiner wanted you to express it as a percentage, multiply that by 100 and it comes out as 40% in this case. Unit SP9 Forces and their effects. So you can see these here are not going to be a main focus, but these parts are. Right, describe with examples how objects can interact at distance without contact, linking these to the gravitational, electrostatic and magnetic fields involved. So that's what we'll call non-contact forces. And make sure you understand that gravitational, electrostatic and magnetic fields can affect things without actually touching them. That's what that basically means. 1 mark for that. Describe with examples how objects can interact by contact, including normal contact force and friction. Well, a normal contact force is in response to the weight of an object pushing down onto a surface, and it's normal, which means it's at 90 degrees to the surface, and friction would be represented like this. So if the object was moving across to the right, then it would be opposed by friction, which is acting horizontally over to the left. Describe with examples how objects can interact, producing pairs of forces which can be represented as vectors. Remember, a vector has got size and direction, so here's a pair of forces. These 2 forces will be equal in size but opposite in direction. So sorry if this arrow here appears to be a little bit longer. I'll just rub a little bit of it out. And here's your other forces opposing each other. If this arrow going to the right is slightly longer than the arrow going to the left, that means that the object is accelerating over to the right in this particular example. Explain the difference between vector and scalar quantities using examples. Well, that's more like from SP2A. Remember, a vector has got size and direction, a scalar has size only. Here's some examples over here. The vector velocity, its equivalent scalar is speed. Weight's equivalent scalar is mass. And displacement's equivalent scalar is distance, just in case they ask you. Use vector diagrams to illustrate resolution of forces, a net force and equilibrium situations. In other words, it's just using scale diagrams to represent vectors. So they might say 10 newtons equals 1 centimetre. So make sure you take a ruler into the exam with you. Draw and use free body force diagrams. So that's just these here. Not as complicated as it sounds. If you've got 5 newtons of force pushing to the right and 2 newtons to the left, then that'll end up as a resultant of 3 newtons to the right. Explain examples of the forces acting on an isolated solid object or a system where several forces lead to a resultant force on an object, and the special case of balanced forces when the resultant force is 0. So that's just what I've been over. 2 newtons to the left, 5 newtons to the right. You'll end up with just 3 newtons to the right. And the balanced forces, that would just be if you had 5 newtons to the left and 5 newtons to the right, they would cancel out because they're balanced forces, and you'd have 0 newtons as your resultant, with obviously no direction. Describe situations where forces can cause rotation. So they're talking about a moment, which is a turning effect. So you'll have a pivot, you'll have a force acting at a certain distance. That force will be normal or perpendicular. In other words, it means acting at 90 degrees. And from you can see here, recall and use the equation to calculate the moment. So you take that force and multiply it by that distance. So they'll give you the numbers in the exam. Recall and use the principle of moments in situations where rotational forces are in equilibrium. In other words, the sum of the clockwise moments equals the sum of the anti-clockwise moments. So I've done a little picture down here for you. So the anti-clockwise moments equals the clockwise moments. There's your pivot. You can see this object here. It's got a force of 2 newtons and it's acting at 3 meters from the pivot. And it's moving, if you follow the force down, go round the back of the pivot, that is moving in a clockwise direction. And it's 3 meters times by 2 newtons, which is 6 newton meters. And the anti-clockwise, it's a 6 newton force acting at 1 meter from the pivot. So 6 times by 1 is also 6. So this is like a seesaw that is balanced. That just means it's in equilibrium. Explain how levers and gears transmit the rotational effects of forces. Well, you don't need to explain it, it's only worth 1 mark. You just need to know that levers and gears would transmit rotational effects. So in other words, you can make things turn by using a lever or by using a gear. So this here is acting as a lever. You push it down on one side and it goes up on the other side. Explain ways of reducing unwanted energy transfer through lubrication. In other words, apply oil to moving objects, for example a gearbox or a bike chain, and that will reduce the friction, which reduces heat and sound. In other words, reduces wasted energy. Unit SP10, Electricity in Circuits. You've got to be able to describe the structure of the atom, limited to the position, mass and charge of protons, neutrons and electrons. In other words, you've got to know where each of these particles are. So the proton is found in the nucleus. It's got a mass of 1 and a charge of +1. The neutron is found in the nucleus as well. It's got a mass of 1 and a charge of 0. Remember, the p per proton is p positive. The neutron is neutral. The electron is found in the shells orbiting the nucleus. Its mass is negligible, or if you want to be precise, it's 1 divided by 1835, and its charge is -1. Draw and use electric circuit diagrams, representing them with the conventions of positives and negative terminal, and the symbols that represent cells, batteries, switches, voltmeters, ammeters, resistors, variable resistors, lamps, motors, diodes, thermistors, LDRs and LEDs. So they're all over here. So as I say to my students, the positive side of the cell is the big side, because if you add something it gets bigger, and if you take something away it gets smaller. So the small side of the cell is the negative side. Same thing for the battery. That's what that looks like. A closed switch, it's Harry Potter's glasses. Voltmeter, it's just a circle with a V. Ammeter, a circle with an A. Open switch, Harry Potter's broken glasses. See me video if you haven't saw it. Resistor is just a box. Variable resistor is a box with an arrow going through. The arrow is got an upside down V. V for variable. The lamp, it's like an X-Man badge. Motor, just a circle with an M. Diode is D, I, O. That's how I remember diode. A lamp can also be represented as an omega sign or an ohm sign, which is the units for resistance. Thermistor, it's just a resistor but with like a sort of golf club going through it, or you could say it looks a bit like a thermometer. LDR, again, it's a light dependent resistor, so it just starts off as a normal resistor. I like to think you put them on the top of the lamppost, so you better make it waterproof by putting it in a bubble, and there's the sun shining down on the top of it, which changes the resistance of it. And this is an LED, so it's a light emitting diode, so it's just a diode, D-I-O, but it's given off light, so that's the light coming off it. That's how I remember them. Describe the differences between series and parallel circuits. Well, a series circuit has only one loop, whereas a parallel circuit has more than one loop. So this has got one loop, that's got two loops, and this parallel circuit here has got 1, 2, 3 loops. Recall that a voltmeter is connected in parallel with a component to measure the potential difference of voltage in volts across it. So in other words, if we're using this voltmeter here to measure the voltage of this bulb, then you put it in parallel across it like that. Parallel means two things come at once. Explain that potential difference voltage is the energy transferred per unit charge passed, and hence that the volt is a joule per coulomb. Bit waffly. Basically means to get the voltage, just do the energy and divide it by the charge. So in other words, energy is measured in joules, charge is measured in coulombs. They'll often ask you for an alternative unit for the volt, so you could say it's the joule per coulomb. Recall and use the equation energy equals charge times by voltage. In other words, EastEnders is the Queen Vic. That's how I like to remember it. So if you're in England and you've watched the programme EastEnders, the main pub is the Queen Vic. Recall that an ammeter is connected in series with a component to measure the current in amps. So in other words, if your component's there, just put the ammeter either in front of it or behind it, as long as one thing comes after the other. Explain that an electric current as the rate of flow of charge, and the current in metals is a flow of electrons. You just literally got to know that for 1 mark. So the equation is current equals charge over time. In other words, I equals Q over T, and 1 amp would equal 1 coulomb per second, just in case they ask you for an alternative unit for an amp, which can sometimes be a multiple choice question. Same as that one. SP10 continued. You can see that there's a lot of stuff here that's just might not even be on the exam. The main thing to focus here is this green thing, which is the core practical. Right. Recall and use the equation charge equals current times by time. So that's just a case of they'll give you the equation. Remember, you're getting all the equations this year. So they'll just give you some numbers in the equation, just pop them in. 3 marks, thanks very much. Describe that when a closed circuit includes a source of potential difference, there will be a current in the circuit. In other words, voltage causes current. Recall that current is conserved at a junction in a circuit. That's Kirchhoff's law, which basically means what goes in must come out. So the current that goes into the junction, so there's a little junction there, so 4 amps is going in. Basically 4 amps needs to come out. You can see there's another junction here, 2 amps is going in, 2 amps is going in, so that's 4 amps in total. So 4 amps needs to come out. Explain how changing the resistance in a circuit changes the current, and how this can be achieved using a variable resistor. So if they ask you what does a variable resistor do, well, like any resistor, it controls the size of the current in a circuit, and if you can vary the resistor, that means you can vary the current. Recall and use the equation voltage equals current times by resistance, so that's good old Ohm's law. Explain why, if two resistors are in series, the net resistance is increased, whereas if two resistors are in parallel, the net resistance is decreased. So the current has to go through both of these resistors because there's only one path to travel down if they're in series. So 5 plus 5, that's the same as a 10 ohm resistor, as you can see up here. Whereas if you have got resistors in parallel, there's two paths to travel down, so that gives them extra paths to go down, which makes it easier to go down. And if it's a 5 ohm and a 5 ohm, that would be the equivalent of 2.5 ohms. You don't need to be able to calculate the value for resistors in parallel anymore at GCSE. That's just at A level. Calculate the currents, potential difference and resistances in series circuits. So just using Ohm's law, we'll rearrange it. Its current is voltage over resistance if you need to work out the current. If you need to work out the voltage, just do the current times by the resistance. And if you need to work out the resistance, you do the voltage divided by the current. Explain the design and construction of series circuits for testing and measuring. This is your standard test circuit. You need an ammeter in there, you need a voltmeter across the component, and you need a way to adjust the current and the voltage, so we use a variable resistor for that. Now this all ties in with the core practical. Core practical, so this is the main thing. Construct electrical circuits to investigate the relationship between potential difference, or voltage, current and resistance, for a resistor and for a filament lamp. And you've got to be able to test the series and parallel circuits using resistors and filament lamps. In other words, we're using Ohm's law, V equals I times by R. So for 6 marks, you need to tell the examiner, how would you obtain the resistance for this component so that you could plot a current voltage graph? Well, as I've just said before, you'll need a way of measuring the current, I, you'll need a way of measuring the voltage, V, and you'll need to know a way of getting multiple readings. So varying the current and the voltage by adjusting this variable resistor. In order to calculate the resistance of the component, tell the examiner that you'll use this equation here. Get the resistance, just do the voltage over the current, and just take multiple readings, changing the variable resistor each time in order to get 6, I would say a minimum of 6 different readings, and then you can plot your graph. Explain how current varies with potential difference for the following devices and how this relates to resistance. So in other words, you've got to know the IV graph for a filament lamp, a diode and a fixed resistor. So the IV graph for a bulb, or as I like to call it, a spurb, looks like an S shape. Mind, it's only an S shape if you've got both the positive and the negative current and voltages. A diode, you get a massive resistance in the backward direction, so you get 0 current, and then once you get to about 0.6 volts, the current starts to go up in the forward direction, and that's because the resistance is smaller in the forward direction for a diode. And finally, a fixed resistor, well, it'll have a fixed resistance, so it'll have a fixed slope. Remember, to get the resistance, you just do the voltage over the current. If you've got a steep slope, that means you've got a small resistance, and if you've got a flatter slope, that means the resistance is bigger. Describe how the resistance of a light-dependent resistor varies with light intensity. So you'll often see a graph of resistance up the side and the light intensity across the bottom. So in other words, if it's dark and if it's bright. Well, when it's dark, you've got a big resistance on the LDR, and as the light gets brighter and brighter, the resistance decreases. So you get a smaller resistance. Make sure you know that it's not linear, it's a curve. Describe how the resistance of a thermistor varies with change of temperature for negative temperature coefficient thermistors only, which basically means if the temperature goes down, the resistance gets bigger and vice versa. So you'll see it represented as resistance up the side and the temperature along the bottom. When it's cold, the resistance is big, and as the temperature increases, the resistance decreases. So that's what it means by negative temperature coefficient. And that's your symbol for the thermistor, remember. And again, it's non-linear, so it's basically exactly the same shape as it was for the LDR. Recall that when there is an electric current in a resistor, there is an energy transfer which heats the resistor. That's basically just for 1 mark. Alright, current makes resistors get hot. Explain that electrical energy is dissipated as thermal energy in the surroundings. That's what we said before. When electrical current does work against the electrical resistance. In other words, resistors get hot when current passes through them and the heat transfers off to the surroundings. Explain the energy transfer in 10.22 above as the result of collisions between electrons and the ions in the lattice. So in other words, resistors get hot because as the current tries to go through the resistor, the little electrons bump into the metal ions in the resistor, and that causes friction, which causes heat. It's only worth 1 mark, so I'd be very doubtful if you need the explanation I've just gave you. Explain ways of reducing unwanted energy transfer through low resistance wires. Well, that's it for 1 mark. Use low resistance wires if you want to reduce unwanted energy transfers. In other words, if you want less heat in a wire, make sure the wire is nice and thick. Describe the advantages and disadvantages of the heating effect of current. That's what it should say. So the heating effect of current is good, so it's an advantage if you want the device to get hot, for example, a heater or a hairdryer. And the heating effect of a current is a disadvantage in any device not designed to get hot. So your phone or a PC, you don't want them to get hot, but they will because current's in them. So that's obviously a disadvantage. You've got to go and buy yourself a fan if you've got a PC to make sure it doesn't overheat. Unit SP10 continued. It's probably the biggest unit from the entire 2-year course. You can see a lot of this is just yellow, and then none of this stuff here is going to be on the exam. So basically you've got to be able to use the equation. Energy transferred equals the current times by the voltage times by the time. I like to say Emmerdale equals ITV, which is a channel in England that Emmerdale is on, which is a telly program. Describe power as the energy transferred per second and recall that it's measured in watts. Recall and use the equation for power. So power equals energy transferred divided by time. Explain how the power transfer in a circuit device is related to the potential difference across it and the current in it. In other words, power equals current times by voltage. There's another equation you need to know as well, which is the power equals the current squared times by the resistance. If you're wondering where that comes from, if we've got P equals I times by V, and remember V equals I times by R, that was Ohm's law, we can substitute this V and pop in I times by R instead. So P equals I times by R, and let's just clean that up. So that would be I squared times by R. So that's where it comes from. But remember, for 1 mark, if it does pop up on the exam, you're just going to have to use it. You're not going to have to derive it or anything like that. Most of this yellow stuff will not even be on the exam. It'll just be what's in green. Unit SP11, static electricity. You can see all of this stuff here is green, so it's all going to be on your exam. Explain how an insulator can be charged by friction through the transfer of electrons. So If you were to take an insulator, such as a plastic rod, and rub it with another insulator, such as a cloth, friction causes electrons to transfer or jump from one insulator to the other. Explain how the material gaining electrons becomes negatively charged and the material losing electrons is left with an equal positive charge. So in your exam, if it says there's a positively charged object, you know that it's lost electrons, and if it is a negatively charged object, you know that it's gained electrons. A common mistake that people make is to think because something is positive, it must have gained protons. Well, that's impossible. The positive charges, the protons, can't move. They are in the middle of the atom, right in the nucleus. So I like to think when you rub an atom, it's the outer part of the atom you're rubbing, which is the shells where the electrons are. So it's only electrons that can move from atom to atom. Recall that like charges repel and unlike charges attract. So these are both negative, so they're like charges and they'll repel, negative and negative. These are like charges as well, positive and positive, so they'll repel, and opposite charges will attract. Just like magnets, north and south, opposites attract. Explain common electrostatic phenomena in terms of movement of electrons, including shocks from everyday objects. So they are caused when electrons transfer and build up and then you touch something. Lightning, well, that's when hot air rises and cold air falls, and the air rubbing against itself causes electrons to be transferred. They build up in the clouds, and then once it gets big enough, there's a discharge of electrons that comes down as a lightning strike. And attraction by induction, such as a charged balloon attracted to a wall, and a charged comb picking up small pieces of paper. So this is electrostatics. If you rub a balloon against your head or something, electrons will get transferred. In this case, it looks like the balloon has gained electrons because it's became negative. Now, I haven't rubbed the wall, but because I put the negative balloon next to the wall, all the electrons that were at the surface of the wall move deeper into the wall. So the electrons repel deeper into the wall. And that means that the positive charges get left behind at the face of the wall. So now the uncharged wall has gained an induced charge. And that's how the balloon sticks. Because remember, opposites attract. If you rub a comb, you'll charge the comb. Once again, the comb looks like it's gained electrons. So there'll be another object somewhere that's lost electrons, and that'll be positive. Now, if you put that charged comb next to paper, well, remember, paper is made of atoms, and all atoms have got positive and negative charges. So the positive charges that's in the little bits of paper, they will get attracted towards the charged comb. The little negative electrons in the paper will be on the back surface of the paper. They'll go deeper into the paper, just like what happened to the wall. So although you haven't charged the paper directly, it has got what we call an induced charge. It's became charged without you even doing anything. Explain how earthing removes excess charge by movement of electrons. So earthing is basically when you provide the electrons with a path to the earth, usually via a metal conductor, like a copper wire, and it allows the charge to discharge. I'll talk about that more in a second. So that's it, earthing. It's removing the excess charge by allowing the electrons to move. Explain some of the uses of electrostatic charges in everyday situations, including insecticide sprayers. So with an insecticide sprayer, you charge your spray gun negative, let's say, which means that when you spray it, all the little droplets come out with a negative charge. Now, the farmer doesn't have to go around rubbing all the plants. That would be absolutely ridiculous. But remember, the plants will get an induced charge simply by another charge coming close to it. So the plant will have positive and negative charges. All the little negative charges, the little electrons, will be repelled away to the bottom part of the plant, and that'll leave an overall positive charge at the top of the plant or on the top of each leaf, and then the insecticide spray will get attracted to it. Opposites attract. So negatively charged insecticide droplets or spray gets attracted to naturally occurring positive charges in the plant. Describe some of the dangers of sparking in everyday situations, including fueling cars, and explain the use of earthing to prevent dangerous build-up of charge. Basically, petrol is flammable. If you allow electrons to build up, there'll be a spark and there could be an explosion. So you ask yourself, well, how can the electrons build up to create a spark? Right, well, if you are refueling an aeroplane or a car, you are putting petrol through a pipe. And when one thing rubs against another thing, electrons can get transferred. And if they get transferred and they build up, it could cause a spark, which would blow up the aeroplane. Right? So what you do is you get a copper earth wire, and before you start pumping the fuel, connect an earth wire from the refueler to the object that you're fueling up. And if any electrons do get transferred, well, either whatever charge gets built up on the plane, you'll get the same charge building up on the refueler. And so there'll be no motivation for the electrons to jump. So there'll be no spark because the charge over here will be the same as the charge over there. And then what you'd have to do is discharge the charge, usually by using an earth wire. Or even better, at the same time as you use the copper connecting wire, just also connect the wire to the earth, and then charges won't even build up in the first place. Define an electric field as the region where an electric charge experiences a force. Right, so if we've got this charged object here, this negative object, all of these red lines are that negative object's electric field. Now, do you know that a negative object, the field goes in to a negative object? If it was a positive object, the field comes out. Right? It's the same way as a magnetic field comes out of the north pole of the magnet and goes in to the south pole of the magnet. So it's the same sort of concept. Now, if you put a little charge inside that electric field, it will experience a force. Now, because this charge is negative and the main charge is negative, it's a negative electric field, so these are going to repel away. And if you've got a positive charge here, then obviously that's going to get attracted. Describe the shape and direction of the electric field around a point charge. So that's what it is. It's a charge at like a single point. And between parallel plates. So these are the parallel plates down here. And relate the strength of the field to the concentration of the lines. So like I say, that's a point charge. Now if you look here, these lines are close together. So the field lines are concentrated here, close together. So the electric field is strong. Now that's both there and there. So it doesn't matter if it's a negative field or a positive electric field. Whereas if we move a little bit further away from the point charge, you can see that these lines are more spaced apart. So the electric field lines are not concentrated here, they are far apart. So the electric field is weak here. And I've also done it over here on the positive point charge. So that's exactly the same as magnets. Because remember, at a north and south pole of a magnet, the magnetic field lines are very close together, and that's because that's where the magnet is the strongest, at the poles. Now if we look at a uniform electric field, you'll notice that these lines are equidistant apart, which means equal distant apart. It's what we say a uniform electric field, because the lines are equally spaced out. And electric field lines always come out of the positive charge and go into the negative charge. So just like before, make sure if you've got to draw one of these uniform electric fields coming out of parallel plates, make sure that your lines obviously are all parallel, and make sure the direction of the arrow goes from the positive to the negative. Explain how the concept of an electric field helps to explain the phenomena of static electricity. So, electric field, static electricity, well, it's the same rules apply. Opposite charges attract, like charges repel. So objects that are statically charged have an electric field around them and hence can attract or repel other objects, just like I've explained up here. And that's SP11. Unit SP12, Magnetism and the motor effect. So you can see these are green, these statements here. So there's a good chance they'll be on the exam, but not much chance that these yellow ones will be, or just a little bit if they are. Recall that unlike magnetic poles attract, just like that, and like magnetic poles repel. So a north repels a north, a south repels a south, and a north and a south will attract. Describe the uses of permanent and temporary magnetic materials, including cobalt, steel, iron and nickel. Well, the first thing is, make sure you know that they are the 4 magnetic materials that you'll need to talk about at GCSE. And the uses, well, the uses of permanent magnets. For 1 mark, you use them in a fridge door, or for separating recycling, like steel cans from aluminium cans. And uses of temporary magnets could be maglev trains, which is magnetic levitation trains, and electromagnetic cranes found in junkyards and places like that, where they've got to move metal from one place to another, and they use temporary magnets. What they mean by that is electromagnets, so they can turn them on and off. Explain the difference between permanent and induced magnets. So a permanent magnet is always magnetic. Well, that's easy, isn't it? It's always got a magnetic field around it. But an induced magnet, they are only magnetic when in another magnet's magnetic field. So if you just had a piece of iron, it wouldn't have its own magnetic field. But if you put that piece of iron next to a magnet, it'll gain its own magnetic field from the permanent magnet. So the permanent magnet goes north-south. The induced magnet would also be north-south. So make sure you do the north next to the south. I've got videos on my YouTube channel in all these different playlists if ever you need any extra help. Check out the full videos. Describe the shape and direction of the magnetic field around bar magnets and for a uniform field, and relate the strength of the field to the concentration of the lines. Now that's what I've just explained with the electric fields. So with a bar magnet, you've got the lines are closest where the poles are. So the magnetic field is strong here because the lines are close together, exactly the same here. And the magnetic field is weak on the outer edges over there and over here, further from the magnet. And that's because the further away from the magnet you get, the weaker the magnetic field is. We represent the strength of the magnetic field by the lines. And the magnetic fields come out of the North Pole and go into the South Pole. Describe the shape and direction of the magnetic field around a bar magnet and for a uniform field. So for a uniform field, you'd have this plate here and this plate here, which are parallel to each other. and you'd have a uniform magnetic field lines equally spaced out going from the north to the south. Notice around the edges here, it's not quite uniform, so it's just this part right in the middle between the two poles. Describe the use of plotting compasses to show the shape and direction of the field of a magnet and the Earth's magnetic field. So the field around a magnet, what you basically do is just put plotting compasses all over the place. You can see I've strategically placed them to show that the field comes out of the North Pole and goes into the south. So these compasses here would show the shape and direction of a magnetic field. And what you do is you just, whichever way the compass is pointing, draw a little arrow coming out of the compass on the paper next to it. Little arrows coming out like that. And then you just connect all those arrows together there, connect all these arrows together there, and just do the same coming down that way. I've got a video that shows you how to do it if you don't understand what I'm talking about. And the Earth, where the North Pole is and the South Pole is, there's exactly the same field coming out of the Earth. But obviously it's not horizontal like that. The poles would be vertical. Explain how the behaviour of a magnetic compass is related to evidence that the core of the Earth must be magnetic. Well, basically, a compass points to Earth's North Pole. That'll get you 2 marks. Describe how to show that a current can create a magnetic effect around a long straight conductor, describing the shape of the magnetic field produced and relating the direction of the magnetic field to the direction of the current. So you want to use the right hand grip rule for a straight wire. So point your thumb up, point your fingers round like that. Your thumb shows which direction the current's going as it's going through the wire. In this case, the current's going upwards. And the fingers would show which way the field goes. Now the magnetic field direction is from north to south, same as usual. Knuckles is north. And fingertips is south. So if you pointed your thumb up, your fingers would come around in a circle like that. If you were looking down on it, it would be anti-clockwise. And the current is conventional current, which is from positive to negative. Now I'm probably telling you far too much detail because it's just yellow. Recall that the strength of the field depends on the size of the current and the distance from the long straight conductor. Yep, if you increase the size of the current, that'll make it a stronger magnetic field. And if you are closer to the wire, you'll have a stronger magnetic field. So a strong magnetic field next to the wire and a weak magnetic field as you move further away from the wire. You can see these lines here are close together, but these lines further apart are further apart. We always use the lines to represent the strength of magnetic and electric fields. Explain how inside a solenoid, so that's an example of an electromagnet, which is basically just a coil of wire. That's what a solenoid is. The fields from individual coils add together to form a very strong, almost uniform field along the centre of the coil. That's that there. And they would cancel out to give a weaker field outside of the coil. All right. So the magnetic field from here interferes with the magnetic field out there, and you end up with a weaker field out here and a weaker field out there, and nice and strong in the middle. And you'll notice, yes, it's nearly uniform because these yellow lines that I've drawn for the magnetic field are nearly parallel to each other. Notice that the right hand grip rule for the solenoid is different to the right hand grip rule for a straight wire. The thumb this time doesn't represent the current, it represents the direction of the magnetic field, and the fingers this time represent the current, where the current's going. So the current's going from the front of the screen to the back of the screen, front of the screen to the back of the screen. Well, you can see these fingers are coming from the front down to the back. But it's only worth 1 mark, so you'll not need to know that. Recall that a current carrying conductor placed near a magnet experiences a force and that an equal and opposite force acts on the magnet. Well, that would be the same as placing two magnets together. So if you placed a magnet inside this magnetic field, it's going to repel or attract. Explain that magnetic forces are due to interactions between magnetic fields. Yeah, that's just a statement. Recall and use Fleming's left-hand rule to represent the relative directions of the force, the current, and the magnetic field for cases where they are mutually perpendicular, which means all at 90 degrees. So Fleming's left-hand rule is this here. Your thumb represents the movement, first finger represents the magnetic field, second finger represents the current. I've got a nice video on that if you want to know more, but you don't really need to know more because it's yellow. Use the equation F equals Bill. So that's the force on a conductor at right angles will equal the magnetic flux density times by the current times by the length. So if it is on your exam, they'll just give you the equation and the numbers and just pop them in. And explain how the force on a conductor in a magnetic field is used to cause rotation in electric motors. That's just a statement. Unit SP13, Electromagnetic Induction. You can see these bits are yellow and the rest is definitely going to be on the exam in green. Explain how to produce an electric current by the relative movement of a magnet and a conductor. First of all, on a small scale in the laboratory and in a large scale generation of electrical energy. Right. Well, in the laboratory, relative movement just means as long as one thing's moving relative to the other. So you can either push a magnet into a coil of wire or you can move the coil of wire around the magnet. And if you move the magnet constantly in and out, as long as there's movement, then a current will be generated. And if you want a large scale generation, just use a bigger magnet and a bigger coil. Recall the factors that affect the size and direction of an induced potential difference and describe how the magnetic field produced opposes the original charge. I think that's supposed to mean change. So remember, potential difference creates current. So what they're basically saying is, how can you use this setup to get a bigger current? Well, the current will be bigger if the magnet is moved faster, or if you move the coil faster. Also, you'll get more current and more induced potential difference if you use a stronger magnet, or for a third mark, use more coils. Sometimes they'll ask, how do you reverse the direction of the current? Well, the current will reverse if the magnet is reversed or if the movement's reversed. So in other words, if you push the north in, you might get a positive current, and then as you pull the north out, so you've reversed the direction, you'll get a negative current. Or if you're shoving a north in and you get a positive current, well, if you flip that magnet round and you shove the south in, then you'll get a negative current. So if you reverse the magnet or if you reverse the direction, you'll reverse the current and also reverse the induced potential difference. They normally don't ask you about the potential difference. They normally ask you about the current. Explain how electromagnetic induction is used in alternators to generate current which alternates in direction, AC, and in dynamos to generate direct current. Well, it's only worth 1 mark, so if they say, how do you produce alternating current, you say you use an alternator. And if they say, how would you produce direct current, you say use a dynamo. Explain the action of the microphone in converting the pressure variations in sound waves into variations in current in electrical circuits, and the reverse effect as used in loudspeakers and headphones. Well, for 1 mark, you just need to know that a microphone converts sound into electricity, or more specifically into an electric current, and you just need to know that headphones and loudspeakers are the opposite. In other words, you put current in to them and they produce sound. Explain how an alternating current in one circuit can induce a current in another circuit in a transformer. So basically, you need to say that alternating current is put into the primary coil of the transformer. That creates an alternating magnetic field in the iron core, and then that creates an alternating current would be induced in the secondary coil. So here is your transformer. So you put alternating current into the primary, that creates an alternating magnetic field in the iron core, and then that creates an alternating current coming out. If it's worth more than 3 marks, what you say is an alternating voltage creates an alternating current, and then that creates the alternating magnetic field, which creates an alternating voltage, which creates an alternating current. Transformers only work with alternating current, by the way. You can't use direct current. Recall that a transformer can change the size of an alternating voltage. So, you've got 2 types of transformers, a step-up transformer and a step-down transformer. Whatever it says it does, that's what it does to the voltage. So if it's a step-up transformer, it steps up the voltage. Now, as a consequence, the current would get smaller, because the amount of power that you put in has to equal the amount of power that you get out. So if you're putting a small voltage in and getting a big voltage out, you'll end up getting a small current out. Now, to identify a step-up transformer, it's got more coils on the secondary. So if it's a little person, just say that's 10 coils, I think that's 10 feet high. And then if that's 20 coils, that's like 20 feet high. So how do you go from 10 feet to 20 feet? You've got to step up. You have to step up. And a step-down transformer, well, whatever it says it does is what it does to the voltage. So it steps down the voltage. In other words, it takes the voltage and it makes it smaller. So you'd put a big voltage in and you get a small voltage out. Now, how do you recognize a step-down transformer? You've got more coils on the primary this time. So if this was 20 coils on the primary coil, it's only 10 turns on the secondary coil. That's like from 20 feet down to 10 feet. So you've got to step down. That's the way I like to think about it. Use the turns ratio equation for transformers to calculate either the missing voltage or the missing number of turns. So you've got to say that the voltage across the primary divided by the voltage across the secondary equals the number of turns on the primary coil divided by the number of turns on the secondary coil. In other words, the ratio of the voltages, this here, is equal to the ratio of the turns. So they'll always give you 3 of them and you've got to work out the 4th. Explain why in the national grid electrical energy is transferred at high voltages from the power stations and then transferred at lower voltage in each locality for domestic uses, as it improves the efficiency by reducing heat loss in transmission lines. So that's basically the national grid is over here. So you've got your power station, and what they do is they massively increase the voltage. So at the power station you'd have 25,000 volts. Now that might sound like it's already a large voltage, but what they'll do is they'll step it up to 400,000 volts. Now remember, if you step the voltage up, and in this case you're making it 16 times bigger, that means that you're making the current 16 times smaller. And remember, it's the current in wires that makes the wires get hot. So if you can make the current little, that means the wires are not going to get as hot, which means you're not going to have what we call line loss, which is when you're wasting electrical energy because it's turning into heat energy and it's dissipating to the surroundings. Explain where and why step-up and step-down transformers are used in the transmission for electricity in the national grid. So if we look at the national grid again, at first, next to the power station, we've got a step-up transformer. So as I've just said, it goes from 25,000 volts up to 400,000 volts. Now you can't put 400,000 volts into someone's house. So if you step it up, if you step up the voltage at the start, you've got to remember to step the voltage back down at the end by using a step-down transformer. So here's some of the finer details. A step-up transformer steps up the voltage, that makes the current smaller so the transmission wires don't get hot. It reduces electrical energy being wasted as heat energy and dissipating to the surroundings. It improves the efficiency. And when the heat energy does dissipate to the surroundings, you call that line loss. So if you use that phrase in an exam, that'll get you a mark. And then the step-down transformer. Sometimes they step it down a couple of times before it gets to the house. But this is just a simplified version of it. So a step-down transformer steps down the voltage to a safe level for the consumer. Now sometimes they'll ask you, what is the voltage for the consumer? Well, if it's just a house, we have 230 volts in the mains in England. If it's a factory that the electrical energy is going to, they'll either have 11 kilovolts if it's a small factory, or 33 kilovolts if it's a large factory. Use the power equation for transformers with 100% efficiency. So we're assuming that we're not losing any energy. So basically, the power that goes into the primary coil equals the power that comes out of the secondary coil. Remember, power is voltage times by current. So the voltage on the primary coil times by the current on the primary coil is going to equal the voltage on the secondary coil times by the current on the secondary coil. It's over here. So what goes in, the power that goes in, has to equal the power that comes out. But that is only assuming that the transformer is 100% efficient. So they might give you 3 of these things and you've got to work out the 4th. So make sure you can rearrange the equation. Explain the advantages of power transmission in high voltage cables using the equations in 10.29, 10.31, 13.7. Okay, so this will be a 6 marker. And the way that you use these equations to explain what's happening with power transmission in the national grid is like this. Now, every time that there's a bullet point down here, you could potentially get 1 mark. So you don't have to remember all of this, just remember 6 of it. Now, I've tried to use all of these equations. So, long transmission wires have got a large resistance. So, these transmission wires here, going across the pylons, they're obviously miles and miles long, going across farmers' fields and all that type of thing. So, long transmission wires have large resistance for 1 mark. That means you'll end up with a reduced potential difference at the destination for 2 marks, because thermal energy, heat energy, is dissipated in the transmission wires for your 3rd mark. Now that'll be per second. So power, remember, is energy over time. So I've used that equation there. Now that's the problem. So highlight the problem first. All right, that's going to create a power loss. So refer to this equation at that point. Power equals I squared R, or power equals I times by V. Now the solution of that problem, remember, is by stepping up the voltage first. So it steps down the current so you don't waste your energy. Now how do you say that to the examiner? You tell them transformers are used to step up to a high voltage for the transmission. So you could use this equation at that point. Ratio of the voltages is the same as the ratio of the number of turns. So this means you'll get a low current if you've stepped the voltage up. So at that point, just write VP times by IP equals VS times by IS. Let the examiner know that you understand that the power that goes in equals the power that goes out. So if you have put a small voltage in and you get a big voltage out, that means that your current was probably bigger when you first put it in and the current that's coming out is smaller. So you'll end up with a power loss that's smaller because the wires are not getting as hot. So the transformers used to step down to a safer voltage for the consumers at the other end, and that's because the consumer wires are shorter, and so the power loss is less of an issue. Alright, what they do is they'll step the voltage down, which of course means they're going to bring the current back up. So at this point you're going to end up heating the wires up, but that's alright because you step it down at the last minute as close to the consumer as possible. So yes, there's going to be some heat loss in these wires, but the heat loss is less of an issue because the wires are shorter. Alright, I hope that's alright for 6 marks. Unit SP14, particle model. This is probably going to be on the exam, this will be on the exam, these probably won't, or if they are, just 1 mark. Use a simple kinetic theory model to explain the different states of matter. So remember, that's solids, liquids and gases, in terms of the movement and arrangement of particles. So here's your 3 states of matter, solid, liquid and gas. Now your particle arrangement, you say that the solid is in nice neat rows, you get fixed volume, fixed shape, and the particles are very close together. As a result, the density will be very high. And how do the particles move? Well, by vibration only, because they're bonded together. The particles in a liquid are irregular, which means they're all over the place. They've still got a fixed volume, but they don't have a fixed shape. They'll fill the shape of the container. And the particles are close together as opposed to very close in the solids. How do they move? Well, the particles move slow and randomly. Particles in a gas are irregular, so it means they're all over the place. Not a fixed volume this time. A gas will fill the volume of the room. It's not a fixed shape either, and the particles are far apart. How do the particles move? Rapid and random. Or if you don't like the word rapid, just say fast and random. Recall and use the equation. Density equals mass divided by volume. So we use a wiggly P for density, M for mass, V for volume. Core practical. Investigate the densities of solids and liquids. Now this is going to be one of the core practicals, so it's worth 6 marks. So let's have a good look at this. So if you're going to investigate the density of a regular solid, for example a cube, well, always base your explanation on the calculation. So to get the density of whatever, you need to know the mass and the volume. Tell the examiner you'll use this equation. Tell the examiner that to get the mass, you'll use a mass top pan balance. And to get the volume, because it's a regular shape, you just do the height times by the width times by the depth. So just use a ruler. In order to get the density of an irregular solid, so that means like an odd shaped solid, again, tell the examiner you're going to use density equals mass over volume. Now you can get the mass once again just by using a mass top pan balance, so it doesn't matter that it's a funny shape. You can still put it on the top and you'll get the mass. However, this time to get the volume, what you'll need to do is take a measuring cylinder, so tell the examiner that, and fill it up with water to say halfway, and then plop the shape into the water and the water will rise. Now if we say the volume at first was volume 1 and the volume after you've put the object in is volume 2, Then to get the volume of the irregular shaped solid, just do volume 2, take away volume 1. And that will also get you anything up to 6 marks. Now, if you're going to get the density of a liquid, well, get a measuring cylinder, put it on top of the mass top pan balance, and then press the tare button to take it back to 0. When you put your liquid into the measuring cylinder, the mass top pan balance will just tell you how much mass of liquid there is. And the beauty of this is at the same time, the measuring cylinder will also tell you the volume. So you just get the mass and the volume by using the mass top pan balance using that technique. Explain the differences in density between the different states of matter in terms of the arrangements of the atoms or molecules. So specifically to do with the density, solids, the density is very high, liquid density is high, and gas density is low. So with the exception of water and ice, most solids are more dense than their liquid variant. And as they turn into a gas, so that's another physical change, generally the particles spread out even more. Describe that when substances melt, freeze, evaporate, boil, condense or sublimate, mass is conserved. So that just means the mass that goes in equals the mass that comes out. And that these physical changes differ from some chemical changes because the material recovers its original properties if the change is reversed. So sometimes if you have a chemical change, the properties will be totally different and you can't reverse it. But if you're just changing the state of matter, that's just a physical change. And if you reverse the change, you'll get the same properties back. So if we start with solid, go into a liquid, go into a gas. A solid melts and turns into a liquid, and then it evaporates or boils and turns into a gas. If you cool the gas, it'll condense to form a liquid. Once you've got the liquid and you cool it, it'll freeze to a solid. When it's a solid, it doesn't have much energy. When it's a liquid, it's got more energy. And when it's a gas, it's got high energy. And sublimate is when you turn from a solid directly into a gas without going into the liquid state of matter. Explain how heating a system will change the energy stored within the system and raise its temperature or produce changes of state. So that's what I've just said there. The solid has got a low amount of energy, a liquid's got medium amount of energy, gas has got a high amount of energy. You know, you could be asked that in your exam, you get 1 mark for each of those things. Define the terms specific heat capacity and specific latent heat and explain the difference between them. So remember, it's only worth 1 mark. Well, specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree C. Specific latent heat for 1 mark in an exam, it's the amount of energy needed to change 1 kilogram of a substance from one state to another without changing its temperature. In other words, specific latent heat is what you use if there's a change of state. Specific heat capacity is what you use as you're heating one state and it's getting close to either the melting point or the boiling point. Use the equation. Change in thermal energy Q equals the mass times by specific heat capacity times by the change in temperature. Now, you'll have to rearrange that sometimes in order to find the specific heat capacity. So if you know how much energy you're putting into a liquid or a solid, and you know the mass of the liquid or solid and how much it's changed its temperature by, then you'll be able to work out what the specific heat capacity of the solid or the liquid is. Use the equation Q equals M times by L. So that's the amount of thermal energy needed for a change of state. and that's the mass times by the specific latent heat. Explain ways of reducing unwanted energy transfer through thermal insulation. In other words, wrap up something in foam or put a lid on it if you don't want to waste thermal energy from that thing. 1 mark for each of those things. Now here we go, here's the 6 marker, this is your core practical. So this will definitely be on the exam. Investigate the properties of water by determining the specific heat capacity of water and obtaining a temperature time graph for melting ice. So, here's how to determine the specific heat capacity of water. You'd need to fill a container with a known mass of water. And for another mark, measure the starting temperature of the water. For your 3rd mark, use a heater connected to a joule meter to heat the water. Measure the final temperature of the water. Measure the amount of heat energy used. And then calculate the specific heat capacity by using C equals Q divided by mass times by temperature change. The temperature change will be the final temperature. Take away the temperature at the start. I've got a nice little video all to do with that. Definitely recommend you watch it. Obtaining a temperature time graph for melting ice. Right, what you do is you tell the examiner that you would heat some crushed ice. You'd record the temperature and the time. So say heated for 10 minutes, record the temperature over the 10 minutes. And then use those results to plot your temperature time graph. Now what you should find is when it's ice, it'll start to heat up and heat up. Now once it changes from ice, which is a solid, into water, which is a liquid, during the melting process, you should end up with a flat part of the graph. It's what we call a plateau. And that's because it's changing state. Now you're still putting energy in because you're still heating it. So you say, well, where's that energy gone? Because the temperature's not going up. The energy is being used to break bonds, turning it from a solid into a liquid. Once it's fully turned into a liquid, then the temperature will continue to go up. Once it reaches a change of state again and changes from a liquid into a gas, once again you'll end up getting a flat part, which is your plateau. Now these plateaus, because there's no change in temperature, that's when you'd use this equation here. Q equals M times by L. You'll notice there's not a change of temperature involved when you're using the specific latent heat as it's changing state. As it's changing the temperature, and this section here and this section here, that's when you would use the equation for specific heat capacity, which does involve the change of temperature in the calculation. Again, if you're not sure about that, check out my video from the SP14 playlist. Explain the pressure of a gas in terms of its motion of its particles. You just need to say that the pressure of the gas is because of the motion of the particles. Pressure is caused by collision of particles. For 1 mark. Explain the effect of changing the temperature of a gas on the velocity of its particles and hence the pressure. Well, if you increase the temperature, that's going to increase the velocity of the particles and that's going to increase the pressure. And it does say for a fixed mass of gas at a constant volume. Describe the term absolute zero minus 273 degrees C in terms of the lack of movement of particles. So just make sure you know that the coldest temperature you can ever get is called absolute zero, and it's at minus 273 degrees C. And at that point, there's no movement of the particles, or it's very, very minimal. And therefore, if the velocity is zero of the particles, then there'll be no pressure either. It's only worth 1 mark though. Convert between Kelvin and Celsius scales. So if it does ask you to do this, to convert degrees Celsius into kelvins, take the degrees Celsius and add 273 to it. For example, if you've got 27 degrees C, that'll actually be 300 Kelvin. And to go from kelvins into degrees Cs, you take 273 away. So if you had 300 Kelvin, that's actually just 27 degrees C. Explain that gases can be compressed or expanded by pressure changes. So if the pressure gets bigger, the volume of the gas will get smaller. So in other words, if you squash it, a balloon will get smaller. You know, that kind of thing. Explain that the pressure of a gas produces a net force at right angles to any surface. Well, it's just a statement for 1 mark. Explain the effect of changing the volume of a gas on the rate at which its particles collide with the walls of its container, and hence on the pressure produced by a fixed mass of gas at constant temperature. It's similar to what I said up there before, but this time we're changing the volume. If you change the volume of something, if the volume increases, that means that the rate of collisions between the particles is going to be less, because they've all got more room and they're not as squashed up against the walls either. So therefore, if there's less collisions, there's less pressure, and vice versa. Use the equation P1 V1 equals P2 V2. So they'll just give you 3 values. You've got to work out the 4th, so make sure you can rearrange equations just in case it's on. And explain why doing work on a gas can increase its temperature. Well, you just need to know that if you do work on a gas, so remember work is force times by distance, so if you are pumping up a gas by putting a force on it, that'll make the gas get hotter, for 1 mark. And finally, SP15 Forces and Matter, the last unit. Now the 2 videos put together are 2 years worth of work in year 10 and year 11. So if you're still here and you've watched the whole thing, well done. You're giving yourself a really good chance of doing well on the exams. Now we don't need to know any of this stuff, it will not be on your exam, and we don't need to know any of that either. So we just need to concentrate on this little bit here and then we're done. Explain why atmospheric pressure varies with height above the Earth's surface, with reference to a simple model of the Earth's atmosphere. Right, so if we've got the Earth's surface here, imagine you had a great big mountain. Well, down at sea level, all right, down at where the ground is, you've got lots of air pushing down, so the person experiences a large atmospheric pressure. The higher that you go up the mountain, right, you're going towards space, I guess, there's not quite as much air above your head as what there was when you were lower. So if there's not as much air pushing down on you, so there'll be a lower atmospheric pressure. So in other words, the greater the height, the lower the atmospheric pressure. That's why people who climb to the top of Mount Everest, there's less air up there. So you've got to take your own oxygen tank up with you. That's one way of thinking about it. Describe the pressure in a fluid as being due to the fluid and the atmospheric pressure. Right, well, imagine you're a little fish. So not only do you have the water pushing down on top of you, creating a pressure, but you've also got the atmospheric pressure as well. So 1 mark for saying that perhaps, and 1 mark for saying that. So pressure due to a fluid pushing down, and also being deeper means a greater fluid pressure. So this fish here is deeper, so there'll be a greater pressure on it compared to that fish there. I mean, it's obvious really. This fish hasn't got as much water on top of it pushing down. This fish has got a lot more water on top of it pushing down. Recall that the pressure in fluids causes a force normal to any surface. Well, whenever you see the word normal, you know it just means 90 degrees. So fluid pressure pushes outward in all directions, putting a force on all surfaces at 90 degrees. So if I pricked the water balloon here, water would squirt out that way. If I pricked a hole in the balloon here, water would squirt out that way. So it doesn't matter where I put a hole in the balloon, water would squirt out at 90 degrees straight out of the water balloon. So that proves that fluid pressure pushes out in all directions, putting a force on the surfaces at 90 degrees. Explain how pressure is related to force and area using appropriate examples. First of all, let's base it on the equation for pressure. So pressure equals force over area. So if I have a little look at this, common examples, we use a high heel shoe. So the high heel of the shoe has got a small area, so force is concentrated, which creates a high pressure. Now if we explain that mathematically, whatever the force is of the person, their weight is being concentrated in a very small area. So mathematically, if this number on the bottom gets smaller, then this number over here gets bigger. So you get a high pressure if the force gets concentrated in a small area. Now the opposite of that would be something like a snowshoe, which has got a large area. So the force is spread out, which creates a low pressure. Again, let's look at it mathematically. So pressure equals force over area. So if it was the same person, it's the same force because it's the same weight. But this time, their weight is getting spread out across a large area. If this number on the bottom gets bigger, it makes this number on the top get smaller. So it's a low pressure because it's a bigger area. And this is exactly how I tell my students to explain it. You get 3 marks for that. You'd get 3 marks for that. Describe how pressure in fluids increases with depth and density. So in other words, the deeper that you go, you've got pressure increasing. You get a high fluid pressure at the bottom and you get a lower fluid pressure at the top. And the reason for that is because there's less weight or force of water pushing down if you're close to the surface, and you get a higher fluid pressure at the bottom because there's more weight or force of water pushing down on you. Now what about density? Well, a less dense fluid, that'll have less particles pushing down. So if you've got a more dense fluid here, just look at how many more particles, right? We'll do the same depth. So that depth there and that depth there. But if you were down here, you've got a lot more particles pushing down on you. So that's why there's a higher fluid pressure at the bottom of a more dense fluid compared to a lower fluid pressure at the bottom if it's only a less dense fluid. That's because there's less particles pushing down on you. I hope you understand that. And I've created the same depth because I was changing the density. I've kept the depth the same. Just like over here, I was changing the depth, so I've kept the density the same. These are both in the same fluid. And finally, you've got to be able to use an equation to work out the pressure due to a column of liquid. So in other words, if there's a column of liquid above this little fish, how would you work out the pressure on that fish? And how would you work out the pressure on this fish? Right? You'd need to know the height of the column of liquid. So in other words, that could be the depth, multiplied by the density of the liquid. And then you multiply that by gravity, the gravitational field strength on Earth. And there you go. So that's it. It's all done. Now remember, your exam's usually about a third calculations, a third short explanations, and a third long explanations. Well, I hope that's helped you there. Good luck with your exams. They're getting very close now. Work hard, be nice, and bye for now.